Everyone, my name is David. I'm a mechanical engineering student. Today we'll be doing physics 2 for engineers. It can be either biomedical engineering, mechanical engineering, industrial engineering, chemical engineering. I'm a little bit cold today, but today we'll be going over the subject of resistance. So what is resistance? Let's say we have some sort of wire, of conductive wire. I have one as an example here. You can see it's a copper wire. Basically, if we charge this wire, if we give it some sort of current, let's say this is a positive side and this is the negative side. Usually the electrons will want to move from the positive charge to the negative charge in order for it to be in equilibrium. So we have electron jumping like this, like this, like this, like this, all this E. They're jumping until they get here. That's what creates the current. The current, we sign it by the letter I. So what do we mean by that? What is resistance? We don't have a conductor that is ideal. Every type of conductor has some sort of resistance. We don't have the ideal conductor which gives out. Each electron here moves at the same speed and at the same, it doesn't lose its energy, let's say, its potential. We don't have like someone that goes like at the fast of light. The current doesn't go at the speed of light, I mean. So, what happens in a resistor or a resistance, what it means is we have some sort of conductor, right? Let's say the opposite. We have an electron, let's say this is its optimal movement. See, it's big, it's fast. So what the resistance is, it goes slower and takes up more space. Like this. Let's say this took 2 seconds to charge. This one took a whole like 10 seconds. Which means its resistance is pretty big. Pretty big. But how do we compute resistance? Well, pretty sure Max Faraday or someone of that era has figured out a way to compute it. We have R, which is resistance, is equal to rho 0 for vacuum times the length of it, the length of the whole resistor, dividing by its surface area. If we have either a resistor that's built like this, a square resistor, this would be the length, this would be the length, this would be the surface area, this would be A. And rho 0 is a constant of the same material. Let's say we have copper. So its rho would be a little bit different. Its rho would be like, let's say, rho of R or something like that. It wouldn't be that rho 0. So I'll write up a quick example I had in one of my tests, and we'll try and solve it using our form. But before that, if we have like some sort of interchangeable, a material that's combined of two materials, or a conductor that's combined of two materials, we'd want to have the differential equation for that. So let's say we have our formula again, rho 0 times the length divided by the surface area. I'll write it here. Rho 0 constant, L is the length, and A is the surface area. Surface area. So, if we derive it to get the differential form of the equation, we get that d of r is equal to rho 0, which now is a constant, but it may be interchangeable, like in the example we're going to do, times the change in length that we have dot dl divided all by the change of surface area dot dividing by dA. So if we want to rewrite our formula for this one, which is not the simple form, we have r is equal to the integral on rho times dl dividing by dA. That is our formula. That is what we're going to use most of the time. So remember this formula, guys. It's going to be very important. I'll write up my example question and we'll start solving it. So after a little bit of briefing over on the theory, we have this example right here. We have x going in that direction, the positive side is going into there. We have y going upwards. And we're given that we need to compute the total resistance of this cylindrical resistor in the length of L, but it has an interchangeable rho. The resistance per unit of length is changing here, right at the center of the half. So at the first half, up until we get to the half point, which is L over 2, we have this rho of x, and after that, until we get to the finish line here, the L, we have this one. So what do we do from here? Let's write our formula first. We have r is going from here, rho of x dot dl over dA. Let's think. Let's think about it as R1. Why? Because we can think of it as two resistors connected in series. If you did high school physics, pretty sure you've seen all this drawing, right? Of a resistor. Let's say this is R1, this is R2. And this is what we have exactly here. They're connected in series. We have this one's gonna be up to here to the half point. It's gonna be R1, and from there to that end point of L, it's gonna be R2. Both have might have the same resistance, but it's changing throughout the entire cylinder. So we'll think of it as R1. The first step is gonna be R1. So what do we do from here? We can set the dl to be dx because we move in the x direction. So let's rewrite it. We have R1 is equal to, what's our rho of x here? It's going to be rho 0 over a times L over 2 minus x dot dx, all that over dA, put it in an integral. I'll delete it because I want to show you some pretty neat stuff. Okay, we have a cylindrical body. We use cylindrical units, not units, I mean variables. I forgot their name in English. Cylindrical variables. So what we have here, let's say we have dA. We want to compute just that integral right now. So in cylindrical forms, the Jacobian, the J, is going to be r times sine of theta times d phi dr d theta. What does it mean to you guys? We divided, no, it's without the d theta, it's without the d phi, I mean. It's just like this, r sine theta dr d theta. So we get that we go from 0 to r on dr, right? Then we have another integral, let's time it, going from sine of theta, or is it r d theta and that's it? Not exactly sure. No, it's without the sine of theta. It's just r dr d theta without sine. My bad, guys. I got confused with spherical coordinates. Yeah, this is the word coordinates. I remembered. Coordinates. So, our surface area in cylindrical coordinates should be r dr d theta. And d theta goes from 0 to 2 pi because we have a whole circle. d theta. What do we get? We get r squared over 2 times 2 pi. That goes out. We have pi r squared. R big R squared, because it goes from 0 to r. Interesting. So we solve this, we can put it right here. So we have r1 over r, oh my bad, rho 0 over a, all that, dot dx, divided without the integral now, we have the answer, which is pi r squared. So we can see that r0 and a are also a constant. We're given it. I didn't write it here, but we're given that there are constants. So let's write r1 now is equal to, we can take it out of the integral and just leave the integral on the sum over the axis coordinates. So we do rho 0 over pi times a times r squared. And you integrate, let's see, we go from 0 to L over 2. So 0 to L over 2 in the first half. And whatever is written here in the brackets, L over 2 minus x dot dx. Pretty interesting. Now that's a pretty simple integral if you ask me. We just do this. We just, let me copy it here, pi a r squared times, now we integrate it. What's L over 2 by dx? It's just L over 2 times x minus x squared over 2, all that ranging from 0 to L over 2. Now you just put L over 2 and 0, you substitute them. So we have r1 is equal to rho 0 pi a r squared times L over 2 times L over 2 minus L over 2 squared like this over 2. Now, that's a pretty basic algebra, but I'll write it, I'll solve it with you guys. I need to delete here, I'll delete the cylindrical coordinates, Jesus. I'll delete it and I'll solve it right at the top. So like this, we go from here to here. We have L over 2 by 4. I'll multiply this constant afterwards. So we have L over 2 divided by 4, L squared divided by 4, minus, what do we have here? L squared over 4 over 2. And it should be equal to L over 2 over 4 minus this. From here we get L squared over 8 times our constant, which is rho 0 pi a r squared. That's the first half, that's r1. Pretty interesting, pretty interesting. It's nothing really too complicated right now. So, we'll leave it there. I'll delete this so I can create some space in order to solve for R2 now. So, like this, because we want to keep the board beautiful. So R2 is the integral of rho of x, let's say rho 2x over dl, which is again dx, is going to be over dA. So we do see the geometry is pretty much symmetrical. Does it really mean it's equal to this? I'm not sure, because these two seem to be this like around the same variable. But if we didn't have to, we couldn't know if we didn't have these similarities. It could be x minus, I don't know, L to the 8th. So, we'd have to compute it in order to be sure. Sometimes you can rely on symmetry. But right now we'll just do the whole integral again. So we have, oh my god, I deleted the a. rho 0a times xl minus 2 now over dx and that over dA. Integrate it. We already know this one's known. We already know these two are constant, so we can take them out of the integral now. We can do it just like this, rho 0 pi a r squared again. Now, over integrated xl minus 2 like this. And now we go from L and a half, half an L, all the way up to L, because we're on the second half of the cylinder. Now, what we do, we have this pi a r squared times, let's integrate it, this one's x squared over 2 minus L over 2 times x, all that from L over 2 up to L. So we have r squared, our second resistance is going to be that constant, but let's solve for this now. I'll do the solution to this right at the side here. This is our R1, I'll just circle it around. So, let's do it. This one's L squared over 4 over 2 times, minus L over 2 times, oh, wait, I got confused. It's L squared over 2 minus L2 times L. We can see that this one should be, yeah, it should cancel out, I'm pretty sure. This is our first half minus, because now we put L squared here. L squared over 4 over 2 minus L and a half times L and a half. Just like this. This one goes to 0. And from here we get L to the second minus L to the fourth minus sign outside. So from here we get also L squared over 8, because this one's gonna be negative L to the L over 8, and we have a negative sign here coming from the integral, so it's gonna be L squared. So let's put it back here in the final solution of the second resistor. Rho 0 over pi a r squared times L squared over 8 again. So as I said, we have this. We have R1 and R2 are connected in series, right? So let's just combine between them and we get the overall total resistance. So RT equal to, excuse me guys, 8 pi a r squared plus rho 0 L squared 8 pi a r squared. We get rho 0 L over L squared over, this becomes 2, this stays 8. From here we can just say it's rho L squared over 4 pi a r squared. This is our final solution, guys. This is our total. So, it might have been a little bit long, but nothing too crazy really. It's pretty simple. They are pretty simple integrals. So, really hope you enjoyed, find it informative. I'd appreciate if you left a like. See you in the next lesson, I guess. This was Physics 2, Resistance, and we did an example from one of my tests. So, you see, the tests are not too hard in this course, but they're a little bit time consuming. See you in the next one.